60-second adventures in thought. Number 5. The twin paradox. Albert Einstein didn't have a twin brother, but he had some funny ideas of what you could do with one. He imagined two identical twins. Let's call them Al and Bert. Now, Al is a couch potato, but Bert likes to travel. So he hops into a spaceship and zooms off at close to the speed of light. That's when Einstein's special theory of relativity kicks in. It says that the faster you travel through space, the slower you move through time. So from Al's point of view, Bert's time would be moving slower than his own. To put it another way, time might fly when you're having fun, but when clocks fly, they run more slowly in relativity. After a while, Bert decides to head back, still at close to the speed of light, and returns to his brother with his holiday snaps. But when Bert arrives home, Al will now be older than his twin, which makes their double dates a lot more awkward. Although it seemed implausible, Einstein just followed his theory to its logical conclusion, and it turns out he was right. This concept of time dilation provides the basis for our global positioning system, which is how your sat-nav knows you need to turn left in 200 yards.
Why is that called twin paradox? Where is the paradox? How does this turn into a paradox?
Well, because from each of their point of view, they're both traveling at the same speed. So why would the time be different?
Absolutely correct. You reverse out 10 points. The speed is relative. All right, so which one is traveling near the light speed? According to the Earth-bound observer, twin in space is traveling near the light speed. According to the twin in space, the Earth is traveling near the light speed. All right, guys, so the speeds are relative. If that's the case, how do you know who's going to be younger, who's going to be older upon return? How do we resolve the paradox? How does the paradox get resolved? Okay, so it depends, right? It depends on who's accelerating. At some point, one of them is moving near the light speed, so the question is which one? You can't tell because motion is relative. But who gets to speed up to speeds near the light speed? The one traveling in space, right? Who gets to slow down from speeds near the light speed to the speed of the stationary observer or the earthbound observer, the one coming from space. All right, so that's how you resolve the paradox. You yourself 2 points for that one. So we got 4 questions. So you're traveling at the light speed with a mirror in your hand. If you were to look into the mirror, would you be able to see your reflection? The answer to that question is, it depends, right? According to Einstein's assumption, or the postulate, light always moves at the light speed relative to you. So that means that regardless of your motion, light is always going to travel at the light speed. What that means is you should be able to see your reflection in the mirror. That's what it means. All right, so the next question is time traveling into the future possible? The answer to that question is, common sense will say no. Can you leap like 100 years into the future within the next fraction of a second? About a million.
Kind of.
Yeah, so what happens? Only if the time kind of slows down, right? So when time becomes relative, and the fact that the time slows down as you start to approach the speed of light allows you to be able to actually time travel into the future. But that sort of time travel will be only one way. You can only leap into the future. You cannot come back to the present or go back to the past. If you're traveling at the light speed from here to New York City, how much of the landscape would you be able to see? The answer to that question is none. So that kind of makes sense because the travel itself would take only a fraction of a second. Along the direction of motion, space is going to contract. So it would turn into a magic trick. You'll be looking at the landscape in Chicago, and by the time you blink, you're also looking at the landscape in New York City, skyline. All right, is it possible for any mass to travel at the light speed or faster? Once again, the common sense will say, why not? Einstein will say, absolutely not. He will say nothing with mass can travel at the light speed or faster. And then we have the problem of neutrinos traveling faster than the speed of light. This is 2011, and so they repeated the experiment a number of times, and every time they repeated the experiment, they discovered that neutrinos were traveling slightly faster than light. So the question became, did Einstein make a mistake? Or is it possible that probably about 1,000 physicists end up repeating the same mistake time and time again? So we'll get back to that question. So special relativity is about motion near the light speed. You're traveling at a constant speed in a straight line. So this is happening at a constant velocity. You don't get to speed up or slow down or change direction. So everything that we've been discussing is true under these conditions. So it's a special case of motion. It's a limited case of motion. It's a limited case of motion near the light speed. So something is going to happen to mass as you're traveling near the light speed. Something is going to happen to time as well as something is going to happen to space. Everything goes back to Einstein when he was 16 years old. Looking at Maxwell's equations, he came up with the question of what would happen if you were to travel at the light speed with a mirror in your hand. Would you be able to see your reflection? Common sense will say no. Einstein saw a way to answer the question is yes. He thought that it was possible for you to be able to see your reflection in the mirror, provided that the light moves at the light speed relative to you regardless of your motion. All right, so he came up with 2 postulates upon which he based this theory. Postulate number 1 is the relativity postulate, which means that you're going to be moving in a straight line at a constant speed. Obviously, in this case, you're moving near the light speed. The second postulate is the postulate that the light travels at the light speed relative to you, regardless of your motion. So if you're at rest, light travels at the light speed. If you're moving at the light speed, light still travels at the light speed relative to you. That's what it means. So if this postulate is correct, you should be able to see your reflection in the mirror. If this postulate is correct, if I'm driving my Ford Tempo at the light speed, if I were to turn on the headlights, I would still be able to see what's in front of my vehicle. That's what it means. All right, so light speed becomes the only constant in the universe in Einstein's theory. Because light speed is the only constant in the universe, what's going to happen is, as you start to approach the light speed, the time is going to slow down for you. Time slows down as you start to approach the light speed, stops right at the light speed. And what happens to space? Space is going to contract in the direction of motion outside of your reference frame. All right, but would you notice that your time is slowing down as you start to approach the light speed? Now imagine that you're inside a spaceship traveling near the light speed, and we're watching live on TV here on Earth. So here's what would happen. Your 1 second will become longer and longer in our reference. So you would start to close.
Any given second.
From our perspective, your light will close on. From your perspective, everything will. Bang, bang. Notice that the time becomes relative. All right, when you're living in that reference frame, 1 second is going to be 1 second long. But if we're watching live on TV, your 1 second maybe is minute long, hour long, day long, 100 years long. Bang, bang. So things will look closer. Boom, 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 boom. How. It's a good commercial and really demonstrates the concept quite well. All right, so Einstein's theories, theory of special relativity, every single aspect of it has been tested and tested and tested. That's a trillion times. When I say a trillion times, I'm exaggerating it. It's probably more than a trillion times. Every time we run a particle physics experiment, you get billions upon collisions. All right, so the dilation of time is something that usually exhibits itself every single time you run the experiment. So every single aspect of Einstein's theory has been tested and tested and tested and tested to be correct. So Einstein's theory is more of a scientific fact, a theory by name only at this point.
But you've got things you have to do now, and so do I. And so, I'm gonna get on this spaceship. And I'm gonna go to Blargon 7 in search of alternative fuels. But when I return, 200 years from now, you'll be long gone. But I won't have aged at all. So you tell your great-granddaughter to look me up. Because Adrian, baby, I'm gonna want to meet her.
All right, so that's Joey from France. So time's gonna slow down. What happens to space? Space is going to contract in the direction of motion, only outside of your reference frame. This was a creative project that I myself had done, probably about more than 20 years ago, actually. When I was taking a Photoshop course over at COD, College of DuPage, I'm illustrating the concept of contraction of space in this project. I think this was my final project. Took the picture when I was living in New York City, obviously. So, and then I tried to demonstrate the contraction of space at half the light speed. If you are traveling from left to right at half the light speed, if you were to look outside, you would see the contraction of space. And the space that you leave behind is going to look reddish. The space that you're moving towards is going to look bluish. This is known as relativistic Doppler effect. In between, you got this greenish grayish haze. And your time would slow down, but you would not notice it. You would only notice the contraction of space if you're looking outside. However, the space on the inside, what would happen to the space on the inside? Do you think that the space on the inside is also going to change? All right, so imagine that you're on an airplane capable of traveling at half the light speed, or 90% of the light speed. If you're looking outside, you're going to be able to see the contraction of space, but would you notice the contraction of space on the inside as well? All right, so if you have to go to the bathroom, assume that the bathroom is about 20 yards away. So what happens when you approach the light speed? Do you think that this spaceship or the airplane that you're on is also going to contract? What do you guys think? Do you just get up and start pissing sideways, thinking that that's where the urinal is, or do you think you will have to walk to the bathroom still?
It would be the same.
Give yourself 5 points. Guys, nothing is going to change within your own reference frame. Everything is going to look the same. If you're located 20 yards away from the bathroom, you still have to walk 20 yards. If you cannot see the outside, you will not even know that you're moving near the light speed. Your time is still going to take 1 second at a time. So everything is going to feel the same. Everything is going to look the same. If you can see outside, you will see the contraction of space. If you're watching something live on TV, as you're moving near the light speed, you will experience the relativistic time dilation effects. All right, so the next question is, what happens to mass? Weirdly, 1905, Einstein solves this problem. And since the paper in for publication, paper contains only three conclusions. Number one, light speed is constant, regardless of your motion. And then what happens is the time gives and the space gives. So there's going to be contraction of space in the direction of motion outside of your reference frame, and the time is going to slow down for an object moving near the light speed. So the question is, why the light speed? What's so special about the light speed? What would happen if you reach the light speed? What would happen if you actually exceed the light speed? All of a sudden, he notices that the light speed is the final speed, which means that it's a constant. Nothing can travel faster than light. So the question is, why not? So all of a sudden, one day he's watching a train go by, a couple of days after the publication of the paper. And then all of a sudden, he notices that there is a reason why you cannot exceed the light speed. All right, so imagine that you're traveling at 90% of the light speed. All right, let me just get out of here first. He notices that if you start to approach the light speed, what's going to happen is the energy that you put in to accelerate something is going to go into the mass of an object as opposed to the speed of an object. All right, so this is your speed relative to the light speed. And this is your original mass, otherwise known as the rest mass. And then M becomes your relativistic mass. So what Einstein is thinking is there's no way for any mass to travel at the light speed, because when you start to approach the light speed, the energy that you put in is going to go into the mass instead of speed. All right, so at 90% of the light speed, my 150-pound mass is going to become about 350 pounds. That's what it means. All right, so as you start to approach the light speed, the energy that you put in is going to start to go into the mass of an object. At 99.9% of the light speed, my original 150-pound mass is going to become more than 3,000 pounds. We're very close to the light speed. What happens to the mass? Notice that it's going to become almost 1,000,000 pounds. So I'm going to be as massive as a train. So the next question is, what would happen if I were to travel at the light speed?
Mass would be infinite.
All right, so mass would become, I don't like these transitions. All right, so what would happen if you start to approach the light speed? All right, so you got C. C divided by C is going to be 1. 1 minus 1 is going to be 0. All right, any number divided by 0 is going to be infinity. So this becomes infinite. Okay, but that's not the problem. The problem is, what is the amount of energy required for any mass to travel at the light speed? So the amount of energy required for anything to travel at the light speed is your famous equation, E equals mc squared. So what happens when your mass becomes, so what's going to happen is you start to approach the light speed, your mass starts to become infinitely large. So the amount of energy required for that mass to travel at the light speed becomes infinitely large. And is there a problem with this? Of course, there's a huge problem with that. What's the problem? Last time I checked, universe is finite in size. What that means is the energy in the universe is also finite in size. What that means is there would not be enough energy in the universe for any mass to travel at the light speed or faster. That's what it means. All right, so if Einstein is correct, nothing with mass can travel at the light speed or faster. It's out of the question. And neutrinos have masses. All right, and that's the reason why they were doing the experiments to figure out what the mass of a neutrino was. They were trying to get an exact measurement on their speeds. They do have no masses. And all of a sudden they discovered that, wait a minute, these neutrinos are traveling faster than light. But then again, Einstein says nothing with mass can travel faster than the speed of light, because the amount of energy required for them to be able to travel faster than the speed of light would be infinitely large. Given the fact that neutrinos have mass, it's out of the question that they would be traveling faster than light. So it was more than likely that these physicists were making a mistake somewhere. So the question was where? All right, so we weren't, at Fermilab, we weren't really impressed with what was going on. And somehow, instead of submitting their work for peer review, these people decided to go to press directly. I think they were trying to get credit for it. And then here's what happened. All right, just pick out the best answer first.
D. D.
All right, D. All right, those of you guys who say D, 5 points. Those of you guys who pick D, 2 points as usual. So nothing with mass can travel at the light speed. The reason is because your mass will become infinitely large, and the amount of energy required for you to be able to travel at the light speed would be infinitely big. The universe is finite in size. So there would not be any energy. There would not be enough energy for any mass to travel at the light speed or faster.